Hi everyone, I'm Peter Naylor, a research fellow at the European Space Agency in the PhilApp. Today I will present a joint work done with Diego Di Carlo and Makoto Yamada, who are also with me at Weekend IAP, and with Arianna Traviglia and Marco Fiorucci from the Center for Cultural Heritage Technology IIT in Ca' Foscari, named Implicit Neurorepresentation for Change Detection. To give some context about our work, it fits in the cultural heritage field and stems from the detection of illegal mortar activities. To assess the damage and stolen goods from historical sites, the detection of looting is the first step to retrieve stolen goods. However, the assessment is currently done by sending teams to likely areas to check if looting has occurred. This manual assessment of looting is costly and difficult, especially if you imagine large remote areas or in countries with difficult geopolitical situations. The scale and precision of these detections requires precise and annotated data, which is largely absent. Hence, the field needs efficient ways to automatically detect and monitor such activities in an unsupervised setting. For this, LiDAR can help. It can scan large areas with high precision, and another advantage compared to satellite imaging is that we can see under the canopies, if they are not too thick, of course, allowing us to monitor archaeological sites in the tropical forest. From a machine learning perspective, we cast this problem to a change detection task with an unstructured data time, which is the cloud point. Here I give you a small sketch. The task is change detection, which means finding relevant differences between two timestamps. It can be wood harvesting, urban sprawling, or looting detection. With height information, this task could be solved by simply subtracting the height between the 2 point clouds. However, this is not possible because the supporting cloud points named x1 and x0 do not match. Indeed, weather conditions and flight path cannot perfectly coincide. The idea of this work is to make the supports match by translating the point cloud into a continuous height shape. Once this is done, we simply look at the difference between these new representations. We give a more concrete view of our pipeline on the right. The first step, explained with the sketch, is the supervised setting, where we regress the height to the input coordinates. The second step utilizes the first representation for change detection in an unsupervised manner. So let's look at the first module. So we use implicit neurorepresentation, which are coordinate-based neural networks, which mean that they take coordinates in input, and they output the variable that we wish to reconstruct. In this paper, the height. These models are named implicit because the shape is implicitly encoded into the weights. As this is a regression task, there's a data fitting term, which is simply a MSE. The learned model is an MLP, and hence we have access to the gradients. Of course, this depends on the activation functions. Having access to the gradients allows us to model the total variation norm, not as a finite difference, but directly onto the real gradients. ENR has been used in many projects such as PINS and NERF due to its high flexibility. I have to mention an important trick about implicit neurorepresentation, which is the random Fourier features that have allowed to reconstruct high frequency. You simply add this layer directly after the input. On the left, we see two ENR reconstructions from the same input. One without RFR, on the left, fails to capture high frequencies, contrary to the other. And finally, the right figure can help shed some light to this phenomenon, where two close points will be more easily separated with the IFR basis. Another model, which is an extension of this, is named Siren, and mimics this trick by having sinusoidal activations. They have a better reconstruction and a much more satisfying Laplacian representation with respect to the gradients. However, these models are quite difficult to train due to the periodicity in the activation layer. So I've given a fast overview of ENR, but how are we going to use ENR in our pipeline? In input, we have the coordinates, in output, the height, and we have the data fitting loss term. I recall what we're trying to do. Simply capture the shape, take the difference, and output a class. The first method is one implicit neurorepresentation with x, y as input. The second method is one implicit neurometer for both shapes with x, y, t as input. This is very useful for three reasons. We halve the amount of parameters, we have a single object to manipulate, and we can manipulate time within the model. As mentioned before, we can use the total variation norm for regularization, and we introduce a similar norm for the temporal aspect. We use the L1 norm to make it sparse, and this formulation translates to, we know that change between the two shapes happen, but in a sparse manner. It allows to fuse both cloud point information, and this is the final loss that we'll be trying to minimize. So now let's look into the unsupervised module. We are going to validate a method on urban sprawling because this is where we have annotated data set, and there are three classes, no change, newly, and destroyed buildings. We expect that for an addition, we get a positive value, and for deletion, we get a negative value of a difference in altitude. We'll be using a Gaussian mixture model, but we could have used two Otsu methods for dividing this mass into three. The idea is that the ENR is doing most of the heavy lifting. On the left, we see the distribution of the height variations, and in the middle, overlaid with the ground truth. And on the right, we have with our trained Gaussian mixture model. It serves simply as a thresholding to separate this mass into three. This is the validation data. It is an urban sprawling data introduced by Degelis and al. In 2021. It's a simulated airborne LiDAR dataset of Lyon with three classes, and it tries to mimic true data with different noises and sensors. On the right, you have the different configurations. Photogrammetry dataset is a low resolution high noise with a tight scan angle. The multi-sensor has the first cloud at low resolution high noise and the second cloud at high resolution low noise. The first ablation study we perform is the use of random Fourier features and siren to capture high frequencies. We noticed that the RFF module outperforms on the change detection task. However, we noticed during training that siren performs better at reconstruction, as expected by the literature. We will see in visual examples a bit later that siren overfits to the noise and to the building borders compared to RFF. We also checked the hyperparameters influence for the total variation norm and the time difference. And we noticed that there's a 6% in IOU to be gained by correctly selecting the hyperparameter. Hence, we choose these hyperparameters by cross-validation. We now present a benchmark of methods with M3C2 and O2 being the previous state of the art, and we only display the best achieving methods for the no feature mapping and siren, because they were underperforming from the previous graph, and display all the other configurations for random Fourier features. We noticed that having a single model for both shapes helps by 2%, and we noticed that the time difference penalty also helps of about 2% as well. We show some visual results. In the first row, we had the first timestamp reconstruction, in the second timestamp, and in the latter, the difference in overlaid GMM predictions. We have a single exception, being the ground truth for the first row and last column. We notice that siren has the least amount of noise, fewer points in the last row, and a smoother reconstruction. However, it overfits on the building borders, which is not the case for RFF that tends to be smoother on the borders. We apply this to the second version of the dataset with more class. We outperform again the previous state of the art on the building detection. We should modify the loss to better take into account the other classes when TD and TVN are not appropriate, especially for vegetation growth and mobile objects. Finally, we apply this to some archaeological example in Cambodia with annotations. We find 3 potential lutein pits with the ground truth and 1 large false positive that can easily be disregarded as no human would dig a 20-meter pit. It is actually a wood farming area. This example shows the effectiveness of our method in tropical areas with canopies. Conclusion. We need high frequencies in the input data, and RFF performs the best. We use a fraction of the number of parameters compared to the previous state of the art, and the best shape reconstruction model is not the best at change detection. If you wish to use our code, don't hesitate. There are 2 GitHub projects for it. Thank you very much for listening.